Hello there. We continue this section of book reviews, and the second one that I'm going to review for you is Unknown Quantity, A Real and Imaginary History of Algebra by John Derbyshire. This is not John Derbyshire's most famous book. It seems he has another one on the Riemann hypothesis, which was his probably most best-selling book, and I think we received some book awards as well. So this book was published by Joseph Henry Press, Washington, and it's relatively big, 374 pages. Okay, so first things to say about this book. What is this book about? Well, like the previous one I've reviewed, this is a mathematics book, but it's also a popular mathematics book. So even if you aren't an undergraduate in the field, you should be able to enjoy this book. It should come with a warning. This is a book that has been designed for a very specific type of public in mind. So it's a history of algebra. We're going to explain in a minute what history of algebra means in the context of this book. It's the information it gives is information that any person with an undergraduate or further degree in mathematics knows all about, so they won't find it perhaps very, very enlightening, although there is a lot of history of mathematics, which is not something that mathematicians are too keen on, I believe. On the other hand, for a completely lay reader who is not interested in mathematics, this book is not for you. Like, it's not impossible to follow. I think its prerequisites are probably some pretty high school level of mathematics, an interest in the field, and maybe some acquaintance from either popular books or maybe one or two courses into some university mathematics. That is, knowing the basic rudiments of abstract algebra, of what a group is, of what a ring is, of what a field is, of what their importance is for contemporary mathematics, will probably take you a long way. So this book really does have a very difficult audience to find because, again, for the lay reader, this is going to be too daunting. For the mathematician, it's probably going to be too trivial. So that Goldilocks zone is really people who are interested in mathematics, but are not full professionals. And I am lucky enough to be in that sweet spot. So I have to say in advance, I enjoyed this book a lot. I consider it one of the best books I've read on the topic and one that I wholeheartedly recommend. Okay, let's take a look at the book little by little then. So the book is divided into three sections. Part 1, the unknown quantity. Part 2, universal arithmetic. Part 3, levels of abstraction. And as I said, this is a history of algebra. And it's pretty chatty. It includes a lot of, if not historical context, historical anecdotes and episodes. It includes some math, but as I said, most of the math is pretty easy to follow without a university education. There are some areas when math starts getting tricky and when you will probably lose the thread. And finally, towards the end, where the mathematics really gets difficult, the author rather wisely just decides to focus on the anecdotic and on the background information about the mathematical figures of the 20th century and their discoveries more than on contents which would be difficult for mathematicians in other areas. So the first block, as I said, unknown quantity, starts exploring. The first block is the history of algebra from its beginnings to about 16th, 17th century. So basically, it starts telling you about Babylonians and the Egyptians, how they start working with equations. And, he talks a lot on how we have tablets from the Babylonians. And in those tablets, we can find solutions to linear and quadratic equations. So linear equations in one unknown, like x plus 3 equals 5. And quadratics, same thing, but with a second degree. So x squared minus 3x plus 2 equals 0. So the Babylonians, and there's a very nice video online that you can see of this physicist, Richard Feynman, talking about Babylonian versus Greek mathematics. So Babylonian mathematics is very applied mathematics. It was, just specific solutions to problems without general formulas or without general methods. So the next big jump in algebra, and algebra at this stage is basically solving equations with unknowns. That's why the section is called unknown quantity after all. The next big leap is Diophantus. So Diophantus, late Greek slash Roman mathematician. We don't know his exact dates, but probably fourth, third, fourth century of the Common Era, living in Egypt. He's the one that really makes the jump. The Greeks had already explored some solutions to algebraic equations using geometry, but Diophantus in his Arithmetica basically creates the field of algebra, and he creates a notation for representing different unknowns and different powers of unknowns in a set of problems. The next step would be Islam. Very characteristic of this book is that Islam gets pretty short shrift, even though algebra is generally considered, from the name itself, al-Jabbar, an Islamic invention and development. Yeah, he doesn't devote much attention, and he doesn't give much importance to Islamic algebra. He basically says the only thing they really did was, write some treatises, maybe organize the different types of solutions to especially second degree equations, some explorations like by Omar Khayyam on cubic equations, equations of the third degree, those that have at least one x to the third power. And but he clearly, is not too keen on that, and he then jumps to Renaissance Europe, and there we have a qualitative jump in that cubic equations and quartic equations are explored, and algebraic solutions for cubics and quartics are discovered. That is, solutions in terms of the coefficients, like in the quadratic equation, x equals minus b plus minus square root of b squared minus 4ac divided by 2a. Those three letters, a, b, c, represent the coefficients of a polynomial. That is, the numbers that go next to the letters, to the unknown letters. Yeah, like in x squared minus 3x plus 2, the coefficients are 1, minus 3, and I think I said 2. Yeah, well, the quadratic equation, the formula must more or less well known with different varieties in the Middle Ages, but it's in the Renaissance when Cardano and a few other mathematicians, Tartaglia, discover the solutions to third degree, a formula that gives you the solutions for third degree and fourth degree equations. And, Derbyshire considers that a big breakthrough. And that leads him also to talk a lot about other aspects, for example, imaginary numbers. So the solution of the cubic equation led to the exploration by Cardano of imaginary numbers, which were first considered like useful but meaningless mathematical abstractions and tools. But, their use in solving equations will become more and more important and will lead in the 18th, 19th century to their coming of age and to their becoming a respectable part of mathematics. And then he ends this section. I'm not going to stop on everything he says and all the mathematicians he mentions, but he ends, talking a little bit about Descartes and his analytic geometry, which unites algebra and basic geometry, and also Viet, and how he explores what are called symmetric polynomials, because those will be interesting and valuable for the second part of the book. One thing that I haven't mentioned in that is interesting is interspersed with the normal chapters which describe history, anecdotes, and facts, there are mathematical primeurs that explore some mathematical area that is going to be developed in the historical chapters. So in the first block, the mathematical primeur explains a little bit about cubic and quartic equations and their solutions. Okay, we continue then with block part number 2, which is called Universal Arithmetic. And this more or less covers from the 17th century, basically from Newton, to the late 19th century approximately, at least in Britain. And this section is called Universal Arithmetic, and the reason is that there is a shift in this period from just solving equations and unknowns towards a more abstract generalization of what solving equations, of what working with unknowns, of what having operations really means. So in general, the path in the history of algebra, as represented in this book, is, the first step, which is part 1, is solving equations. The second one is this greater generalization and study of abstract properties. And the last block, levels of abstraction, is, taking the abstraction to the nth degree. Modern abstract algebra is a very, very, very abstract field of mathematics. But back to part 2. Part 2 starts with Newton and his exploration not of calculus but of algebra. He did some interesting work in what are called symmetric polynomials, which I'm not going to explain, but well, the book gives an easily enough explanation of what they are. And these symmetrical polynomials have also an interesting property which Newton discovered. There are two types of symmetric polynomials, the elementary ones and the complex ones, and you can always rewrite any expression in symmetric polynomials in terms of elementary symmetric polynomials, and this is pretty important. Another thing that is explored here is the fundamental theorem of algebra, which is discovered in like the late 18th century, although most satisfactory proofs are 20th century ones, and a proof is given. The fundamental theorem of algebra basically says it's connected again with solutions of algebraic equations. It basically says that a polynomial equation always has solutions. These solutions might be complex numbers, but there are always solutions to a polynomial equation. And in fact, the number of solutions is the same as the power of the polynomial. And well, there's an ingenious explanation in this book of why the fundamental theorem of algebra is true and why it is misnamed in the opinion of the author. The proof reminds me of one that was made also in a Numberphile video by this very famous mathematics professor. His name is, I have a book of his here. Eisenbad. Yeah, David Eisenbad. So I recommend you watching that video if you want to get a nice explanation of the fundamental theorem of algebra at a popular level. Where else are we taken here? So the attempt at finding solutions, algebraic formulas that give solutions to algebraic equations had progressed from, we said, linear, second degree, third degree, fourth degree. Fifth degree equations, no formula was being found. And the reason why no formula was being found is because there does not exist a general formula. And this is probably the pièce de résistance of this book, the attempt at explaining one of the big breakthroughs of 19th century mathematics and one of the greatest breakthroughs in algebra itself as a discipline, the proof that the quintic equations of the fifth degree, cannot have solutions for all of the quintic equations in terms of a formula that has their coefficients and the basic operations of addition, multiplication, division, taking roots, and so on. So why the quintic can't be solved? That was probably part of the roughest part of the book for anybody who's going to read it. The explanation is not perfectly transparent, but the steps that lead to at least a very general understanding of how this is proven. Remember we mentioned symmetric polynomials. So one thing that was discovered in the 18th century was that if you have an algebraic equation, and that algebraic equation will have solutions. So if it's a second degree equation, 2 solutions. If it's a cubic, 3 solutions. And you can rewrite the solutions in terms, they can be rewritten in terms of all the solutions. So you get one solution, let's call it alpha, and another solution, let's call it beta for a second degree polynomial. You can rewrite this as alpha is equal to something, which will include some roots and addition and subtraction, blah, 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 which includes alpha and beta. And beta can be rewritten in the same way. And the same thing if you have a cubic with 3 solutions, and a quartic with 4 solutions, and a quintic with 5 solutions, and so on. The next step is permutations. So it's experimenting with what happens if you permute the solutions. If you have these different formulas with the solutions rewritten in terms of all the solutions, and if you keep permuting the solutions, changing one solution for another, what happens? Are the formulas still valid? Does the algebraic equation not break down? And seeing that sometimes it does break down, it creates problems. The next step is Lagrange, a mathematician who studies what are called resolvent equations. So using what I have just explained, you can get to a thing called a resolvent equation, which allows you to know or to work with those solutions of all the possible solutions of a polynomial equation and know things about that equation and the solutions. The person who proves that the quintic equation cannot be solved is a Norwegian mathematician, Niels Henrik Abel. And again, not easy to explain the solution and how he arrived at that demonstration. And Derbyshire makes a half-hearted attempt. But the main idea is at least two main steps. Is he makes a proof by reductio ad absurdum, so by proof by contradiction. Basically, Abel starts with accepting that there is a general algebraic formula in terms of the coefficients of a polynomial for the fifth degree equation. If this solution exists, you have to be able to rewrite it as a polynomial in all of the solutions. The problem is this polynomial in terms of all the solutions is a polynomial in 5 unknowns, and polynomials in 5 unknowns can take 2 or 5 values in permutations only. And this apparently, because of other things that other mathematicians discovered before, this leads to the contradiction that no such expression for a general solution can exist. Anyway, as I said, this is the roughest part of the book. I had difficulties understanding it. It's been 2 months since I read the book, so it's not too fresh in my mind. So I'm afraid if you want to know or understand this in a little bit more detail, you'll have to go and check the book yourselves. More things. After that, the book explains the appearance of vectors in algebras. He explores how these new concepts of algebra can be applied to multiple dimensional algebras. In a way, you can see complex numbers as like 2-dimensional numbers because you can represent them in a Cartesian plane as a vector with 2 coordinates on the x-line, which would be the real number coordinate, and on the y-axis, which would be the complex number coordinate. And you can up the ante, and that's what the mathematician Hamilton, the Irish mathematician William Rowan Hamilton, I think, that's what he did with the quaternions, which are 4-dimensional numbers. But the other great development of this section on universal arithmetic is the appearance of matrices. That is explained at the end of the book. 2 things are very important: both the appearance of matrices of linear algebra, which is incredibly useful for modern mathematics, and it's a type of algebra, and also Boole and the English school of mathematics that starts generally following the path that 20th century mathematics will follow in algebra, which is abstraction, no longer considering just solutions to algebraic equations or unknowns, considering any type of operations in any type of number system. In fact, you can use just letters and in any type of operations. And concepts like, which are very important for modern algebra, like the idea of a group, also appear in this period and are developed. Finally, the last part of the book, part 3, levels of abstraction. Levels of abstraction takes us from the 19th century to the 20th. It starts precisely with what we have just left behind, with Galois, who's a French mathematician who can be considered the inventor of group theory. What a group is explained. Modern abstract algebra's foundation includes working with abstract structures that have properties. And these abstract structures are basically sets with objects and with operations in them. So for example, a group is, I'm not going to mention all the axioms, but a group is a set with elements, and and one operation, it could be, imagine, addition, and there are a series of constraints. So for example, when you add 2 elements of the group, when you combine them through the operation, you have to get another element of the group. The operation has to be commutative, that is, a plus b is the same as b plus a. The operation has also it has to be associative, that is, a plus parenthesis b plus c close parenthesis is the same as parenthesis a plus b close parenthesis plus c. There is an identity element, and there are inverses. So this sounds very abstract. If you want to have any information about this in detail, you have lots of YouTube videos that will very simply explain to you what a group is. But the idea is, Galois really pushed the importance of groups as a fundamental concept in mathematics. And then you have building on group, or you also have the concept of a field, which is basically trying to expand a group to 2 operations and not just one. and a field, which is when you can expand a group with two operations and do all the things that you can do, um, and the one operation and the other operation, you get a group except for one tiny small thing. And both groups, fields, and rings are very important in modern mathematics. And well, to wrap up, because this video has been going on for quite some time, the third part, as I said, leads us into the 20th century, and we get basically an explanation of how geometry catches up with algebra all through the 19th century through many interesting developments. And in the end, in the 20th, there is this union of very advanced geometry, very advanced algebra, in algebraic geometry, and in the work of figures like Alexander Grothendieck, which is a great French/German/ question mark mathematician. And yeah, I think that will be the main summary of the book. So the book is a very interesting one, as I said. I recommend it wholeheartedly. I can't understand why this book is not more popular. The only reason I can think of is because it seems that John Derbyshire has some very unsavory political opinions, which probably make him unliked in the mathematics community, or perhaps in the mathematics divulgation community. But the book is pretty marvelous. I learned a lot about algebra, which I didn't know before reading this book. The things that I did know, I consolidated. It was a very, very enjoyable and very entertaining read, even if it sometimes was a bit rough, a bit tough. So, wholeheartedly recommend it. Give it a look, and we'll have another review in a few days' time. Merry Christmas.